All right, in the first video, we talked about increasing and decreasing behavior of functions on subintervals by looking at, in fact, f prime and the critical numbers. So now we're going to learn what the first derivative test is, and in fact, we're going to apply the first derivative test to find a relative extrema of functions. All right, let's get started. So let's say like we have the critical number c, okay? And we know that f is continuous on an open interval containing c. And it doesn't need to be differentiable at the point c. I mean, we still want differentiability on the open interval containing c, but it doesn't need to be differentiable at c. That's okay. So now we're going to classify f of c, so in terms of having a relative extrema. So if f prime changes from negative to positive at C, okay, then f has a relative minimum at the point C and f of C. Okay, so for example, here f is decreasing, so f prime comes with the negative sign till you hit the critical point, and f prime turns its sign to positive because f starts increasing. So that means you make a valley. So at f of c, at c and f of c, you do have a relative minimum. And then the same thing happens here. So here the function is increasing, so f prime is positive, as you see. Okay, and then you hit the critical point, and then the function starts decreasing so that f prime comes with a negative sign. So essentially you make a hill, so the point c and f of c becomes a relative maximum. Okay, so here there are two examples for which you do not have relative minimum or maximum. Because f prime does not change its sign across the critical point. See, like I do have a critical point here, but the function keeps increasing and increasing all the way, so it doesn't make a valley or hill, so I do not have a relative minimum or maximum. And same thing here. F prime is negative, so the function is decreasing, and across the critical point it's still decreasing, so essentially we do not have a relative minimum or maximum value. So the first derivative test says that once you look at your sign chart, if f prime changes its sign from positive to negative or from negative to positive, that means you're talking about a potential relative extremum value at the critical point. All right, now let's try to analyze the first derivative test on the example we have just gone through. Here we go. We have the function x cubed minus 3 over 2x squared. And remember that f was increasing all the way, so f prime was positive here. And we hit the critical point, and then the function starts decreasing, so f prime is negative here. So as you see that we have a relative maximum. So the critical point where you have the horizontal tangent line, you in fact make a hill. So critical point is the point where you have the relative maximum. And the same thing here, f prime is negative in between the interval 0 and 1, and f prime is positive for the interval 1 and infinity. So as you see that you make a valley, and at this critical point we have a relative minimum. All right, now let's have another example. We have f of x equals 1/2 x minus sine x, and we're given the open interval this time. It's 0 and 2 pi, and we're going to find relative extrema. Well, first of all, the given function is continuous on the given interval because sine is continuous everywhere and 1/2 x is continuous everywhere. And we can also talk about the derivative of the function. In fact, the derivative is 1/2 minus cosine x. Now, the first task is to locate critical numbers. We have two kinds, remember. One kind is coming out of setting f prime to 0 and solving for x, and the second kind is to determine if there is any x. That makes f prime undefined, but f prime is 1/2 minus cosine x. It's defined everywhere, so we don't have the second kind of critical number, but we do have the first kind of critical number. So for that reason, we're going to set f prime to 0 and solve for x. Okay, so the equation is 1/2 minus cosine x equals 0. And in other words, cosine x equals 1/2. Remember that we are on the interval 0 and 2 pi. So let me also write this down here. So we're looking for cosine x attaining the value of 1/2. First off, cosine is positive. If this is the interval 0 and 2 pi, just imagine the unit circle. So cosine is positive on the first and the fourth quadrant. So you must have two different options to go with. One is going to be the pi over 3. The other one is going to be 5 pi over 3. In other words, the second one is just coming out of like subtracting pi over 3 from 2 pi so that you land into the fourth quadrant. Okay, so we have two critical numbers, so that means we are going to have three subintervals to determine the sign of f prime. And the first subinterval is 0 and pi over 3. The second one is pi over 3, 5 pi over 3, and the last one is 5 pi over 3 and 2 pi. And we're going to have our sign table to determine the sign of f prime at each subinterval by choosing sample values. Here we go. We have the first interval, second interval, and the third interval. We got test values or sample values from each subinterval. So we got pi over 4, pi, and 7 pi over 4. And what we do next is just to evaluate f prime at the sample points. And it turns out that this one is negative, this one is positive, and this one is negative. So then now we can have the conclusion for f. So now the conclusion is about f, right? So f is going to decrease on the subinterval, increase on this subinterval, and decrease on this subinterval. And remember what the first derivative test says. If f prime is changing its sign from negative to positive, okay, f prime being negative, and in the second interval we have f prime turns out to be positive, so we should expect to have a relative minimum. And here from like across this critical point, 5 pi over 3, f prime changes its sign from increasing to decreasing, so we should expect a relative maximum over there. So now I can go ahead and rewrite this, decrease, increase, and decrease. So we should have a relative minimum at this critical point, pi over 3. And now we should have a relative maximum at this critical point, 5 pi over 3. And now we can plot it, and remember that we started with the open interval 0 and 2 pi, so we have punches here. These are not filled. And we can easily observe that we have a relative maximum and relative minimum happening at 5 pi over 3 and pi over 3 respectively. Now it's the time to practice the content of 4.3. We have really cool examples to be gone through step by step by me in the recitation PowerPoint of 4.3. So if you click on that, you're going to have the first exercise about finding the open intervals for which the function sine x minus 8 is increasing or decreasing. Please check this out. So this is about the first learning objective. The next exercise is about the application of the first derivative test, very similar to the last example in the video. So this time we have 8 minus x times x plus 1 squared. In fact, it's a cubic. And you first obviously find the critical numbers, and then you find open intervals where the function is increasing or decreasing, and then we apply the first derivative test to locate a relative extrema. And there's another example. I intentionally picked this example because it's a piecewise defined function. So on the left of one, the function is linear, and on the right of one, it's quadratic. So you're going to locate the critical numbers. Obviously, one is a junction point. You're going to be careful out there. Okay, and in the next step, we're going to find open intervals on which the function again is increasing or decreasing. And the final step is the application of the first derivative test to identify relative extrema. All right, the final example that, or exercise you call it, that I went through step by step is again the application of the first derivative test, but this time you're given a function sine x cosine x plus 6. So you're going to apply the same strategy. So you're going to find open intervals on which the function is increasing or decreasing, and eventually you're going to apply the first derivative test to identify all relative extrema. So in finding the critical numbers here, you're going to try solving a trig equation. So that's sort of like the crucial part of this exercise. All right, in the second learning objective, we learned how to apply the first derivative test to find relative extrema of a function. And all in all, we're using the data coming from f prime. F prime tells us what the critical numbers are. The sign of f prime tells us where f is increasing or decreasing, and based on that, we determine relative extrema accordingly. All right, that's the end of the video. Thanks for watching. I'll see you in another video.